Okay. So we're doing internal loads. I'm just going to keep going through a few examples, help you get used to this stuff. And I owe you a ton of homework problems on it. So lots of fun is in your future. So,
Okay.
but I want to start today by doing an example. So let's think about this problem. So let's say we have a cantilever beam connected to the wall on the right side, and then a distributed load like this. Goes up to a maximum of 1,000 newtons per meter, and the length is 3 meters. So calculate the internal loads. The easiest way to do this, the way I would recommend doing this, is just imagine going to the other side of this beam, picture what it would look like. The cantilever would be over here. Wait, no, I'm drawing the wrong thing. I'm doing them backwards. Let me draw this and then I'm just going to move them.
Does the cut necessarily have to be from the left?
I would always do it from the left, but it doesn't have to be. Okay, so wait. Okay, so say you have a problem like this. I did it exactly backwards. So the point of that triangular distributed load is on the right. And I'm going to do this calculation, but first I just want to point out that the way I would recommend is imagine walking over to the other side. You have the connection to the wall on this side. And the distributed load like this. And you can see when you do your cuts here on this one, you get a triangular shape. And that's what makes it easier. When you do your cuts here, you get a trapezoid shape. And that's what makes it a pain to deal with. But I'm going to go through it the full way just so you see it. I'm not going to make you do this on homework or anything, but I think it does sort of, if you pay attention to this, you can kind of see how you can break up distributed loads into multiple distributed loads. It can be sort of helpful. Yeah.
What was the time with our distributed loads? They are going downwards onto the beam or the object. What happens if could they be the other direction, going upwards in just a
Yeah, for sure they can be upwards. It's most common that that represents the weight of something, so it's more common to see these pointing downwards. And yeah, they can have horizontal components and stuff too. We don't have time to do that this semester. Sometimes I do that. If you're interested in seeing how that kind of stuff works, it's all in the textbook document that's on D2L.
You on the I remember this. I think trying to remember the title of it exactly.
Well, just the one, I don't know what it's called, but just the one on D2L, the one that I wrote. I don't think it has a very fancy name.
Internal, they want labeled in loads.
Yeah. Okay. All right. So I'm going to do the one on the top, and I'm going to start by the first step is going to be calculating the external loads. So free body diagram of the whole thing. Now I've chosen the whole body to isolate. And so I can, like if we think about this triangle, it has a height of 1,000, a width of 3. That means that the distance to the centroid is 1 from this side, and the area is 1,000 times 3 divided by 2, so 1,500. So over here at the fixed joint, we have a force vector, and we have a couple, I'll call it MR, and then we have a downward force here of 1,500. Newton's second law says Rx, Ry plus 0, negative 1,500 is equal to zeros. And so R is equal to 0, positive 1,500. And then the moment equation, I'll do my moments about the left end. So we have no moment from the R's. We have MR, and then we have a moment arm of 1, a force of 1,500. That force would produce a clockwise rotation, so this is negative. And so MR is equal to 1,500. And now we have to do our cuts. So this whole thing, if I draw out the free body diagram, here's our distributed load. And then we have an upward force of 1,500 and a couple of 1,500. Okay, so are there any points besides the endpoints where you have point forces or point couples or where the distributed load function changes? No point forces, no point couples. The distributed load function is just that line the whole way. So this is just going to be one cut. Okay. Anybody have any questions about that? Anybody get confused about the number of cuts? The other thing, so you can also say, okay, think of all the points that are significant for where these subfunctions can change. There's 2 endpoints. there's nothing happening between them. So we have our capital N is equal to 2. And so there's one, N minus 1 is the number of cuts. There's one cut. 2 minus 1 is 1. Okay, so what's our cut going to look like? I'm always going to go left to right, you know. I'm never going to stop doing that in this class. So my cut is all x values between 0 and 3. And it looks like this. So let's say this is the representative piece. And we're leaving all this stuff off. And so this is the distributed load that we're dealing with. It has a height of 1,000 over here. And then we don't know what it is here yet. We're going to have to figure that out. And we have the upward force of 1,500 and the couple of 1,500. And then T, V, and M. Okay. So how are we going to figure out the height of that line at our value x? So this whole length of this cut is x. Well, we can calculate the equation for this line. So again, we're going to do this as mx plus b. What's the y-intercept when x is equal to 0? What's the height of that distributed load? It is 1,000. You know, we're just trying to come up with an expression for this line, an equation for this line. So here's our there's our line. You know, we're trying to come up with an equation for this. That's 1,000. That's 3. So the y-intercept is 1,000. And the rise over run, well, its rise is negative 1,000 over a run of 3. Y-intercept is 1,000. So this is negative 333.3 repeating x plus 1,000. Yeah, right. So think rise over run. So as you go to the right 3, you drop 1,000. The y position goes down 1,000. Okay, and now we're going to break this up into. So now we're going to think about the geometry of this thing.
One method would be to subtract the triangle that's not in the cut from the whole triangle, I suppose.
Yeah, it looks like you could do it that way. Here's how I'm going to do it. So I'm going to do this. So this is 1,000. And the height over here is negative 333.3 repeating times x plus 1,000.
Is that the height of the bottom rectangle?
Yeah, right. That's this. And so now I'm going to do this as two shapes. We have a centroid here for the triangle, and we have a centroid here for the rectangle. The area of the rectangle is negative 333.3 repeating x plus 1,000 times x. So this is negative 333.3 repeating x squared plus 1,000x. What about the triangle? Well, the triangle, the height of the triangle is 1,000 minus negative 333.3 repeating x plus 1,000. Times x divided by 2. And so the area of this triangle is, the 1,000s cancel out, and you just get positive 166.6 repeating x squared. Okay? So now I'm going to redraw the free body diagram. These areas are the point forces that represent those two parts of the distributed load. I'm breaking up that single distributed load into two separate distributed loads. So here's the piece. And we have the upward force of 1,500, the couple of 1,500 Newton meters. At the midpoint, we have the point force that represents the rectangle. So this is a downward force with a magnitude of negative 333.3 repeating x squared plus 1,000x. And then a third of the way along the beam, we have the one representing the triangle, which is 166.6 repeating x squared. And then we have the internal loads. And now Newton's second law. So we have we have 0, 1,500 for the force at the left end, plus this is a downward arrow, a downward unit vector times this function. So this is 0, negative 166.6 repeating x squared. Same thing with the next one. That's a unit vector of 0, negative 1 times this function. So that's 0, positive 3, we're multiplying 0, negative 1 times this function. So you get positive 333.3 repeating x squared minus 1000 x plus t negative v is equal to zeros. So t is 0. V is 333.3 repeating x squared minus 1000x minus 166.6 repeating x squared plus 1500. And now I'll combine the like terms and you get V is equal to positive 166.6 repeating x squared minus 1000 x plus 1500. Any questions about that part? Yep.
What is the signs of 3.333? They change.
So whenever you have, so a bunch of times in this class, when you have cables or anything, you have an arrow pointing in a certain direction, and then you have a magnitude, something that you're multiplying by a unit vector in that direction. Okay, so that's what this is. It's just that this is a function rather than a number. So we have a unit vector that's pointing down. That's just 0, -1. And we're multiplying that by this function. And so the -1 times this in the y direction switches the signs. Okay. Okay, well, that was the easy part. Now we're doing the moment. That's going to be horrendous.
Oh, we can always just do the verify.
Yeah. So our about point is here. We have a counterclockwise couple of 1500. No moment from the 1500 Newton force. Then we have the 166.6 x squared. That has a moment arm of the whole length is x. And so the distance from the left side to this is x over 3. So we have x over 3 times 166.6 repeating x squared. That would make this rotate clockwise around the about point, so that's negative. Then we have the moment produced by the -333 force. The moment arm for that one is x over 2. The force is 333.3 repeating x squared. So we want the magnitude of this. So negative plus 1000x.
Why can't you take the negative out front and just add it together?
Well, I'm going to just think of it as magnitudes, and then I'm going to think about a clockwise or counterclockwise rotation. Okay. And so that also is a clockwise rotation, so negative. And then plus m minus vx, like always, is equal to 0. And so now I'll simplify this. So we have m is equal to vx, v times x, plus, so I'm going to do, well, I guess I'll do that first algebra term first. So 166.6 divided by 3 is, so this is 5.5 repeating x cubed. And then I'll do that second algebra term. So this is plus, and then, so the plus from this, and then we have the negative in there. So this comes out to be negative 166.6 repeating x cubed plus 500x squared, and then minus 1500. And then we'll multiply what we got for v by x and put that in here. So m is equal to 166.6 repeating x cubed minus 1000 x squared plus 1500x plus 55.5 repeating x cubed minus 166.6 repeating x cubed plus 500 x squared minus 1500. And we have 3 of these cube terms. And 2 of these squared terms. So that is sort of looks to me like I got something wrong. Well, let's just try it, I guess. Oh, these two cancel out. Oh, that's great. So, okay, so we got 55.5 repeating x cubed minus 500x squared plus 1500x minus 1500. Okay, so let's do the derivative checks and see if this is plausible. So dm dx has to be equal to v. Dm dx would give you 166.6 repeating x squared minus 1000x plus 1500. So that one works. And then negative dv dx has to equal q. So negative dv dx is negative 333.3x minus 1000. minus 333.3x plus 1,000, which is what we want, because that is our original Q value, negative 333.3x plus 1,000. Okay, so this one holds. Okay, so that's the answer. And it's definitely like a pain, you know.
So we have to do the second cut?
There's no second cut
Oh.
because yeah, there's
Yeah, the cut goes from here.
right.
Could you show us which one is our Q value?
Yes. So the Q value is that Q function is the height of the distributed load at any X value. So when this is where we calculated the Q value. Okay, because for whatever X you choose, that's the height of that distributed load. And if you have two distributed loads or more than one distributed load, you have to add them together to get your total Q. Okay. Well, that's why you hope not to see these ones where you have to do, where you have to do cuts that make these trapezoids. And if you see them, just picture it from the other side and do it that way. All right. So let's do another example. I'm not sure if we'll get all the way through it, but we'll get a ways into it. So let's say that we have a pin joint at the center of this beam. And a roller at the left end. And 1,000 Newton force going this way. And a distributed load like this. That goes up to a height of 500 newtons per meter. The whole thing is 2 meters long. So this is 1 meter and this is 1 meter. And the mass of this beam is 10 kilograms. And we want to calculate the internal loads. So the first thing we have to do is calculate the external loads. We have a 1,000 this way. We have the roller applies a force like this. I'll call that RA. The pin joint provides a force vector. I'll call that RB. Bless you. There's a weight force down that's 10 times 9.81, so 98.1 newtons. And then for that triangular distributed load, we have a length of 1 meter and a height of 500. This distance is 2/3 of the 1 meter, so this is just 0.6 repeating. And the area is 1 times 500 divided by 2, so 250. I'll put my about point here. It's only once you start doing the cuts that you should always put your about point at the left end. I mean, it doesn't hurt to put it at the left end, but this is a little more straightforward. So Newton's second law. Negative 1,000, 0, plus 0 RA, plus 0, negative 250, plus 0, negative 98.1, plus RBX, RBY is equal to zeros. So we have that RBX is equal to positive 1,000. And RA plus RBY is equal to 348.1. And now the moment equation. The 1,000 Newton force doesn't produce a moment. Its line of action goes right through that point. RA has a moment arm of 1. And would that make it rotate clockwise or counterclockwise around that about point? RA. Clockwise, yep. So negative. And then the 98.1 is, let's do the 250. So 250, what's the moment arm there? It's 2/3 from the left to here, so it's 1/3 of a meter. So 1/3 times 250. Would that make it rotate clockwise or counterclockwise? Right, so this is positive. And then the other two things are happening at our about point, so those are 0. And so RA is equal to 83.3 repeating. And so RBY, plug it into this equation, and you get that RBY is 264.77. So this is 1,000 for the X component, 264.77 for the Y component. Okay, so if I draw a free body diagram, it's going to get a little cluttered, but we have 83.3 repeating here. And at the middle, we have 1,264.77. And then we have the two distributed loads. One is the weight, and the other one is the triangular distributed load. So the weight is this uniform distributed load. And the value of that distributed load is 98.1 divided by the length of 2 meters. So this is 49.05 newtons per meter. And then we have the triangular distributed load like this. It goes up to a value of 500 newtons per meter. All right. So
Should be 1,000 newtons still there too.
the 1,000.
It's pulling out to the left.
Oh, yep. Thank you. Okay, so now how many cuts are we going to need for this? So if you think of the number of these sort of key points for determining the cuts, we know that there's the two endpoints, so we'll start with those. Now, are there any points where, any locations on here, any x values, where there are point forces or point couples or changes in the distributed load function? There's a change in the distributed load function and a point force, right? But those both happen at the same spot at the middle. And so this is just going to be one more point. So we have 3 of those. So we have 3 minus 1, 2 cuts. What? Well, that's just, so I don't know. I go back and forth on which of these ways to think about it, but we're just looking for anything between the two endpoints that have point forces or changes in distributed loads, or more rarely point couples. There's only one point that has that stuff. It happens to have 2 of those things, but it's at the same location. So it's only going to add one more cut to the one that's sort of the default, you know? And so we have 2 cuts. The other way you can think of it is we have 2 endpoints plus one of these other points gives you 3, subtract 1, and it's 2 cuts. Yep.
Professor, if our distributed load, like instead of it being half, it was like a third or a quarter, then we would also need to make a cut where
That's right.
that ends?
Yep, that's right. Okay, so can we do the first cut? Can we finish this? Maybe. So cut 1 is for x values between 0 and 1. And you can think we're skipping all this stuff. So we have this part of the triangular distributed load. This upward force of 83.3 newtons. And then we have the uniform distributed load representing the weight. This is 49.05. And then we have our internal loads. So now let's think about our Q function for this. So what is an equation for that diagonal line? So for the triangle, our equation for the line is mx plus b. When x is equal to 0, the height is 0, so there's no y-intercept. And we can use the full triangular shape to calculate that slope. So it rises 500 over a run of 1. So 500x. Okay. For the rectangle, the height is just 49.05. And so our total Q function is 500x plus 49.05. And now we want to represent these two distributed loads as point forces. So for the triangle, we have a width of x and a height of 500x. And the centroid for this triangle is 2x over 3. The area is 500x times x over 2. So 250x squared. And then for the rectangle, we have a height of 49.05, a width of x. The centroid's in the middle. The area is 49.05x. So I'll redraw this free body diagram now with these distributed loads represented as point forces. We have 1,000 this way, 83.3 repeating up. We have a downward force of 49.05x. And then another downward force of 250x squared. And then T, V, and M. And I guess let's do the calculation next time, and we'll do the second cut too. Any questions about that? Okay.
We have to make this one right here and then one like section where.
Yeah, we only have 2 cuts because to figure out the cuts, you have to look at a full free body diagram before you replace any distributed loads with point forces. So just 2, yep. One representing x values between here and here, and one representing x values between here and here. Yep.